Hey everyone, and welcome to the fourth module of the Introduction to Malware Binary Triage course. Today we will be doing an x86 assembly primer and providing an introduction to the x86 assembly language. First and foremost, what is an assembly language? An assembly language is a representation of machine instructions which are executed by a CPU. These languages are specific to CPU architectures which contain registers, instructions, ways to reference data, and store data. Examples of CPU architectures include Intel x86, ARM, MIPS, and SPARC. In this course, we'll be focusing on the x86 architecture and the x86 assembly language. This architecture is prominently used by malware authors when targeting systems using Intel CPUs. x86 makes use of little endian addressing, which is the ordering of bytes in memory. This will be covered later in this module. x86 provides privilege separation through an abstraction known as ring levels. These ring levels range from 0, which is the highest privilege, to 3, which is the lowest privilege. Little endian addressing is simply a method of storing data within a specific byte order in memory. Little endian addressing stores the least significant byte at the lowest memory address. In this example, we have a 32-bit or D-word integer, which is set into memory, and the least significant byte, D, is stored at the lowest address within the D-word in memory. As mentioned, ring levels are used as a means of privilege separation within the CPU. In Microsoft Windows, all user-land applications run in ring 3, and kernel-level components run within ring 0. In this course, we'll strictly be triaging user-land binaries, and therefore we'll only be dealing with ring 3 privilege levels. The x86 assembly language makes use of registers, which are fast storage locations within the CPU. These registers are made up of multiple sizes. This includes 32 bits in length, which is 4 bytes, also referred to as a D-word, 16 bits in length, or 2 bytes, also referred to as a word, or 8 bits in length, which is a byte. These registers are directly accessed by the assembly instructions in order to perform operations. The general purpose registers include EAX, EBX, and EDX. These contain 16-bit registers AX, BX, and DX, and these each contain 8-bit high registers and 8-bit low registers, which are designated using the H and L characters, as shown in the diagram here. The registers which typically contain source and destination addresses are the ESI register, which is the source address, and EDI register, which is the destination address. This is used in copy operations, and we'll look at an example later on. The register that is typically used as a counter is the ECX register. The register which contains the current stack frame, and we'll be going over what a stack frame is the EBP or base pointer. The ESP register contains the current stack address in memory, and the EIP contains the location of the current instruction being executed. This is one of the most important registers. E-flags are single-bit registers that will designate the current state of the program. An example of this is the 0 flag, which will designate whether the previous arithmetic operation resulted in a 0. This is commonly used in comparison operations. So let's take a look at the assembly instruction format itself. So throughout this course, we'll be using what's called the Intel x86 format for assembly instructions. This differs from what is commonly known as the AT&T syntax, which is a little bit different than this. And we're using this because this is the default syntax for IDA Pro and x64 debug, which are 2 different programs that we'll be using throughout this course. In this example, the raw hexadecimal bytes of the complete instruction are followed by the instruction mnemonic, also known as the opcode, which is followed by the operands for the instruction. Raw hexadecimal bytes are translated into instructions using what's referred to as a disassembler, which are then interpreted by analysts in order to understand the operations being performed by the program, which is what we will be doing in this course. The mnemonics, or opcodes, are symbolic representations of the assembly instruction. In this case, this is the move mnemonic, which represents the move operation. This is followed by the operands used by the instruction. Operands are used right to left in the Intel instruction format. So in this case, the value 1 is being moved into the EAX register. Okay, so let's take a look at some Intel x86 assembly language. So here on the slide, you can see a reading memory example. So here we have a move instruction be performed on the EAX and EBX registers. Since there are brackets around the EAX register, that means that value is being dereferenced, that is stored within the EAX register. So essentially what's happening here is the value that is stored at the memory address that is stored in the EAX register is being accessed, and that 32-bit value is then being moved into the EBX register. Conversely, writing to memory, so we have a writing memory example here. Using the move instruction, we have a value being written to the memory address, i.e. being dereferenced within EAX, and that value being written is hex B33F. So if we wanted to get relative offsets, we would use that instruction mentioned earlier, load effective address. So in this example, if we want to get a relative address to EBX, we would use load effective address with EAX, and then in those brackets, we can perform an arithmetic operation. So here we are adding 32 to the value of EBX. So whatever memory address or whatever value really is stored in EBX plus 32 is now being stored in EAX after that LEA instruction is executed. Conversely, we can dereference a relative offset from a specific address using the move instruction like before. However, within these brackets, we're just adding 32 to the EBX register, and then that value is stored in the EAX register. So again, because these are 32-bit registers, that is a 32-bit value that is being accessed at that register. Now, we will cover what the stack is in detail, but here we have a pop instruction. So this is how data is moved off the stack. And we have a push instruction, which is how data is pushed onto the stack. So here's a copy example. So in order for a copy operation to occur, we have to do a number of setup steps. So in this example, as mentioned earlier, ECX is commonly used as a counting register, which it is here. So we set ECX to 16 or hex 10. And then we are setting the source address of the operation to hex 8B00, and that's being moved into the ESI register. And then as the destination address, we are setting hex 9B00 into the EDI register as the destination. And then that is repeated using the rep instruction with the move operation. So rep takes the operand of another instruction, which in this instance is a move, and then the B denotes the size of the data being moved. So in this example, we have rep move B, which is a byte. So putting this all together, we're going to have 16 bytes because the counter is set to 16 being moved from hex 8B00 into hex 9B00 as the destination address. So basically, we're just copying 16 bytes from one location to another using these assembly instructions. Hopefully that makes sense. Okay, so like all assembly languages, x86 makes use of arithmetic operations very often. So here in this example, we have addition, which is adding 16 to the stack pointer register. Then we have a multiplication, which is using the mul instruction. As you can see here, there is no registers that are being set within the operands. So you would have to have some prior knowledge here, but essentially when the mul instruction is executed with a value, that is how much the multiplication is being done by, and then it is multiplying the value within the EAX register, even though this is not explicitly shown within the operands. Then we have a sub instruction, which in this example is subtracting 16 bytes from the stack pointer. Then we have a division operation, which uses a similar format to the multiplication, where again, this is EAX being divided by 2. And then we have shorthand operations, which are used to increment and decrement, in this case, registers. So we have the increment operation. So we're performing some arithmetic operations within these brackets, similar to the load effective address operations that we were looking at earlier. But basically, we're just incrementing the value stored at that address by 1. And then we have a decrement instruction, which is being used to decrement EDX. So I know some of these might look daunting, especially the increment operation there with the base pointer plus EAX times 4, but that is a very common format. And once you start looking at some of these different patterns, they'll make a lot more sense, and the code that is being executed will make sense as well. So bitwise operations perform operations at the bit level on values, and these bitwise operations are conducted using what's known as logic gates. These logic gates affect the input bits and provide an output. These apply to the same logic concepts that are applied within programming languages, such as logic statements like if and else. For example, the AND operation will only provide a resulting bit if all bits are set, and this is commonly used for a bit mask operation in programs when the provided bits want to be masked out or zeroed. The exclusive OR operation, or XOR, will result in zeros if both the input bits are the same. Otherwise, it will result in a 1. XOR is extremely common in encryption operations since one given input value can be XORed with another input, and the original input can be recovered by performing this operation again. Hence, the second input can act as a key. The OR operation will result in the bit being set to 1 if any of the inputs are 1, and the NOT operation will simply set the bits to the opposite of their current state. The other bitwise operations that are important to make note of are the shift and rotation operations. Shifts will move bits to the right or left and will result in the set bits dropping off the sides of the total value. In this example, the shift to the right results in the bit being dropped off, which results in the value of 0. Rotations, however, will result the bits to the front or the back of the total value. Okay, so let's talk about higher level abstractions used in programming. Functions are abstractions for organizing programs into subcomponents. The functions allow passing of information within arguments, performing operations on those arguments, and returning information. Functions are invoked using the call operation and returned to the calling function using the return operation. Functions use a data structure in memory called the stack. The stack is a last in, first out data structure that is within each thread in memory. The stack stores information about the active function structure of a program. The stack stores the function's return address, i.e., where it is returning after execution, and its local variables while the function is being executed. The top of the stack is pointed to by the ESP register, as mentioned earlier. The stack grows toward lower address space, i.e., from a push instruction, and a stack frame is set up and destroyed for each function call using what's called a calling convention, and we'll go into what calling conventions are a little bit later on. Okay, so let's take a look at an illustrated example as to how the stack operates. So here we have a stack residing in memory. The top of the stack, which is pointed to by the ESP register, is 2F 7F BC4, and the bottom of the stack is 2F FFFC. So you may have noticed that the top of the stack is at a lower address than the bottom of the stack, and this is because the stack grows toward lower address space. So if we write to the stack using a push instruction, we're going to push the value currently in EAX, which is hex DEAD, onto the stack. And doing that push instruction subtracts 4 from our ESP register because it is growing by 4 bytes because a D word is being pushed onto the stack. And it's subtracted again because it grows toward lower address space. So here we're putting that value onto the stack, and now we have that value on the stack first. So then if we perform another push, in this instance, we're going to push the value of EBX, which currently contains 1, then we'll see here again, since we're performing a push, ESP is subtracted by 4 to make room for that new value, and we're growing toward lower address space again. And then that value is taking the place relative to the stack pointer of dead. So now we have 2 values on the stack. We have 1 and DEAD in hex. So now what happens if we perform a pop instruction? So since the stack is a last in, first out structure, when we perform a pop, we are going to be adding 4 to the current stack pointer because we are no longer growing. We're moving towards higher address space because we're popping off a value from the stack. Then that value, because we performed a pop EAX, is changing the value of EAX to 1 that we've popped off the stack. And now that value is removed from the stack. And now the only value on the stack is that hex DEAD. So hopefully that makes sense. The growing toward lower address space makes things a little bit confusing, but basically what we need to keep in mind is that the stack is indeed a last in, first out structure, and this is how it operates in memory. Now, we briefly mentioned calling conventions earlier with respect to stack frames. Calling conventions are a set of rules used to designate how functions are called during a program's execution. They specify how arguments are passed to called functions, and they specify how values are returned from called functions. Here are a number of popular calling conventions, including standard call, fast call, and C declaration. The core differences between calling conventions include how parameters are passed, how values are returned, and what registers are designated for use by calling conventions during its operation. So for example, we have the standard call calling convention where parameters are pushed onto the stack from right to left. This means that the very last parameter of the function call is being pushed on first, and then the very first parameter of the function call is being pushed on last. So if you were to look at the stack, then the first parameter would be the closest to the stack pointer, and then the last parameter would be the farthest from the stack pointer. And in this instance, the call E, which is the function that was called, cleans up the stack. So it removes everything and cleans up the stack before it returns to the calling function. Return values are stored within the EAX register. So for example, if a function adds two numbers together, then those numbers will be returned in the EAX register. And then there are just designated registers for each of these calling conventions. So for example, across all of these calling conventions, those designated registers are the same for specific purposes. And then we have the fast call calling convention, where the first two parameters are stored within ECX and EDX, and the remaining are pushed onto the stack. Like the standard calling convention, return values are set in EAX. And then in the C declaration calling convention, we have parameters pushed onto the stack from right to left, like the standard call calling convention, and then the caller, which is where the function was called from, cleans up the stack, unlike the others. And like the others, return values are returned within the EAX register. So let's take a look at an example of a calling convention. In this instance, we're going to look at standard call, since this is one of the most popular calling conventions used by malware on Microsoft Windows. So here's an example of a stack state when the function hello world is called in the example program. A number of things occur to the stack when the function is called. So these operations occur differently depending on the type of calling convention implemented by the compiler. However, in this example, this is standard call, and the stack operations that occur include the parameters are pushed onto the stack, which in this case is an address to the string that is being printed in the called function. And the return address is pushed onto the stack of where the program will continue execution once the function completes. And the value which stores the base address of the current stack frame is saved onto the stack. In this case, this is the address for the stack frame of the main function. And EBP is set to the base address of the new stack frame, and local variables are stored relative to the stack frame pointer at negative offsets. So if we look at the code example here, we can see that in green, that's essentially saving the scope of the current main function, since all variables are referred to relatively from the base pointer at negative offsets from the main function. In red, we have return 0, which is the saved return address from the main function. And then in yellow, we have the local variables that are within scope of the hello name function. And these are going to be stored on the stack relative to the base pointer, which is within the stack frame of the hello name function. That's all to say that we're trying to kind of put this within scope of real world code to make it more readable, but let's see how it looks in the assembly format. So here is an example of the stack state when the function hello name is called in the example program. However, the assembly is shown instead of source code. The local variables within the given stack frame are highlighted. Here we can see what is referred to as the function preamble, which sets up the stack frame for the function being called. To do this, it pushes the frame pointer of the calling function, or EBP, onto the stack and moves the current stack pointer, ESP, into the new frame pointer register, i.e. EBP. Room for the local character array is made on the stack by subtracting 8 bytes from the stack pointer. This makes room for the str value hell and then o to be stored on the stack. The argument named name is passed to the function and therefore is stored outside of the current stack frame. This, however, is not evident by the disassembly, but the offset to the argument that is stored on the stack is referenced at a positive offset relative to the base frame pointer. But the offset to the argument that is stored on the stack is referred at a positive offset relative to the base pointer, or EBP. The local string variable and argument are then passed as arguments to a subsequent call to printf. Okay, so now let's look at a few more important types of x86 assembly instructions. Control flow operations are performed using flags, which are set by instructions such as CMP and test. CMP stands for compare. Branching operations are performed by jumps, which can be conditional or non-conditional. Conditional branching instructions are affected by flags, such as the 0 flag, which is set by the comparison instruction here or the test instruction here. The 0 flag is then read by conditional branching instructions, such as the jump 0, which will jump if the 0 flag is set, and jump not 0, which will do the opposite. It will not jump if the 0 flag is set. So here's the output of a tool we will be using called IDA-Pro, which will disassemble program bytecode into assembly instructions to be interpreted by a reverse engineer. Here we can see a call made to the Microsoft Windows compare string API, which will compare two strings. The result is then compared to a constant named cstring equal, which sets the 0 flag if they are equal. If the strings are equal, then the branch to the right is taken. If not, then the branch to the left is taken. One of the IDA-Pro views that can be used is called the control flow diagram view, or better known as the graph view, which is shown here. This control flow diagram shows separate nodes within the graph which are separated by control flow instructions. Nodes within the graph are also known as basic blocks. IDA-Pro and its use will be covered in detail in the next module. So here's an example where control flow instructions are used to establish a while loop, where a conditional jump is used to check if a local variable is 0, and this leads to two calls which produce a separate value to check. In order to loop back to the conditional jump not 0, an unconditional instruction is used. The result of the second call within the basic block on the left is used to determine whether or not the loop should continue. Here's an example of using a for loop. The conditional jump greater equals is not taken while the value incremented on each loop iteration, which is incremented using the add instruction, is less than or equal to 10. So with that concludes our x86 assembly primer. I hope everything was clear. If it was not, we're going to be using illustrative examples in the practical labs to help you learn assembly, and hopefully that helps things from here. Thanks so much.